I did my image processing homework there.
Oh, in there.
No, I can listen. Pretty fun.
Yeah, that makes like story time.
Yeah.
They get you to work like an hour almost. You could like
Yeah.
finish the thing.
Yeah. It was a little bit aggravating, but
It's like 10 minutes, huh?
well, I meant like the people in there
Oh,
were pretty like
yeah.
like want something
Yeah.
specific. Not the movie.
Yeah.
What's up?
Stranger, how's it going?
Not bad, dude. We're here in
Other than that, some girls do it. Seen some like I have a one megabyte image. Like it's compressed, and that's only 75 megabytes.
a megabyte image in JPEG.
Yeah. Well, then you can do that on there's no redundant differentiation, no cycle vision.
There must be some for
Consider the raw primary.
oh, raw is still fine.
Well, it depends on how much like a camera you're using and stuff, but they can't do that with raw. But raw image filters aren't that big. They're way time sensitive without the dots.
Well, they still big too.
It means it can go down to a million instead of that easily. I think it was like 5. I'm thinking about like close to 1,000. What's the same for stuff? Yeah, it's sometimes. What was it? Let's go back. Oh, the license. Oh, these are really good. That's plus. Why can't we just do that?
Is it better now?
It's a struggle. A lot of people say that it's
Oh.
Psychology.
X plus. It's
But
like
why
you
don't
start
we
going
use
lower
like
than
a chipset or something?
like let's say like aspect number.
Why?
Alright. So you need to do that.
Okay, let me start by making a few announcements. The restoration lab assignment is due on Friday. April 24th. also need to make some announcements about the presentations um, and the schedule for the rest of the course, because some of you have sent an email. I want to try to remain consistent to what I had announced earlier, so help me remember what I had said or what I put in the handouts. The reports I remember were always due on the 15th of May. That's written down in the handout that I gave you. The question is is about the presentations, the class presentations. What did I say before? Or what did I announce? I recall having it been the last day of the class, which I announced last time or a few times ago, that might not quite happen. Is that what most of the people remember? Yeah. So other than the last day of the class, I didn't say any other variant of that, did I?
So if we don't have time, just have some presentation really quick.
Right. The issue is that the department has a retreat that all faculty are required to attend on Thursday, May 4th and Friday, May 5th. And Friday, May 5th is our last day of class. So I kind of have to make a decision as to, there's few choices we have for Friday, May 5th. Either the whole class gets canceled because I'm not available, or maybe Cindy gives a lecture, or somebody else gives a substitute lecture. In that case, then we will have the presentations on May 3rd. Another option for me is to say, let's just dump the department retreat and just have a regular class, stick to the May 5th schedule of you guys presenting. So those are kind of the two options. So if I have a substitute teaching the May 5th class, or if it is canceled, then the presentations will be due May 3rd, which is even 2 days before. So is that going to cause problem?
Yeah, some of us have conferences to go.
But for both May 3rd and May 5th, right?
No,
You'll come?
if we come back.
Right,
I'm not sure.
right. Anyway, I like my tendency is to just stick to what we announced and just stick to May 5th and just not attend the I mean, despite of how bad it looks to the rest of the department, I think that the class is kind of more important. And this is what we announced. This is what we agreed upon. And my tendency is to just stick to May 5th. I mean, another thing that goes through my head is that if the reports are due on May 15th, I bet a lot of you get a lot done between May 5th and 15th. So one other possibility is to say, okay, let's not have presentations at all. Let's just so that you have really till May 15th to do your best in the project and have more results, etc. And just attach a PowerPoint in your or a 10-page as if it was a presentation. That'll be kind of another option. Um, Yeah. So as of now, I think, but other than the retreat constraint, at your end, there's a group of you that's not available on May 3rd, but is available on May 5th. Is that correct?
I think so.
How many is that?
Probably just me.
Just you. Okay. You know what? Let me just let me do. It's Wednesday now. Let me do some more thinking till Friday. I'll make an announcement on Friday. What day? Does the class have a preference one way or the other? At least the ones who are here.
I kind of like the attachment option.
You like the attachment? Okay. How many people like the attachment idea? Oh my God. Okay. Raise your hands. 1, 2, 3, 4, 5. How many people like the presentation idea?
Well, you still have to turn in a report. I think we all can use practice though, talking about stuff like
Mm-hmm. You're kind of in.
bottom line,
You're in minority, but you have a very good point. I also like to listen to people, and there's some people who never raise their hand, like Alan and Miggs. What preference do you guys have?
It doesn't matter.
It just all
I
right.
mean, sure, I'd rather just hand it in, but like, I don't know.
Right.
Just get
Well,
practice.
you get more of a feedback. See, one advantage of doing the presentation before the report is due is that through this interactive process of me and others listening to your presentation and asking questions, you can actually improve and have some more results by the time the report is due. And then the other thing is, how much progress are you making? Is everything ready by May 5th, or would that additional 10 days buy you a lot more in terms of getting the last minute coding uh, or results done?
What about presentations after May 5th, but before the 15th, like during that week?
That week, I'm in Washington, D.C. and Ohio for 2 government reviews. So that would have been a good choice, but it's just shot. Yeah. Okay. Well, let me do some. Okay. Let me consider all of the input, and I'll make an announcement on Friday while we're done. Okay. So, are there any questions and comments about Way's lecture last Friday? Okay. So, just to kind of um, recap what we're doing. So this is the last kind of module, if you will, of the course. And basically what we're talking about is image and video compression. And I've thought a lot about how to do this last module. I mean, I think about it every time I teach the course. I try not to repeat what I did exactly the last time, simply because things are changing all the time. For example, when I taught the course in 1997, there was no such standard as JPEG 2000, and now there's JPEG 2000, and the standards keep evolving. The new compression techniques come about. In any way, my preference has always been, rather than, I mean, there's 2 approaches one can take. One is just pick a standard like MPEG-4 or H.264 and just explain every detail about it. But the problem is you've spent all your time on that one standard, and you don't really learn about anything else. The other approach, which I think is much better, and that's what we're pursuing, is kind of teach you about the underlying building blocks that go into different standards. Okay, for example, discrete cosine transform is in many standards. It's in JPEG, it's in MPEG-1, MPEG-2, MPEG-4. As of JPEG 2000 time, people have switched to wavelets. So wavelets is another building block, or subband coding, another building block we should concentrate on. So rather than really telling you all the detail in MPEG-4, okay, now this happens, and extreme level of detail, it's best to talk about the concepts and the building blocks that present that are in these different compression techniques. And that includes audio and video, by the way. For example, discrete cosine transform is the basis of MP3, and subband coding is the basis of MP3. So knowing the basics is kind of the best way to go about it. So generally speaking, there are many issues one has to worry about if you're dealing with compression and picking a good compression algorithm. First of all, why do we need compression to begin with? Well, images and video take up a huge amount of space, and if you don't compress it, you're gonna need a huge amount of storage if you're just storing it locally, and you're gonna need a huge amount of bandwidth to get it from point A to point B. And by the way, point A and point B could both be a place on a computer system, for example, from the disk to the display, etc. So in the old days, before the computers were so powerful, you would do a mini compression, and then just the last minute before you displayed it, you uncompress it, so that you don't chew up the I/O buses inside your computer system or any other device you're dealing with. So really the roots of image compression go back to 1960s, where JPL sent these Cassini project and various other ones to space. They would take pictures of space and they had to transmit it. And there you're really bandwidth limited and power limited. If you didn't compress, your entire satellite budget or entire spacecraft budget, power budget, would go into sending the bits out. So it was pretty important to do compression, and that's really the guys like Kesselman, who have the book on image processing, come from JPL and from that background of having to compress. And also there's a little bit of a difference between images and video. Let me backtrack. So one of the key factors in deciding what compression technique to use is what's called compression efficiency. You start with a file of size A, you compress it to size of file B, and there's basically two ways of doing that. One way is what's called lossless. That means file B is the exact same representation of file B. File B and A are the exact same representation of the same thing. And if you compare the reconstructed output of these two things after you compress it, they're identical. No bits were lost. So, for example, I could have a digital movie that Steven Spielberg built, and he absolutely refuses any of his movies to be compressed in a lossy way. He insists on lossless compression, and so you pass it through a box that compresses it in a lossless fashion. You get a new file, then you pass it through a decompression, and you get exactly what you started off with. No fidelity lost. That's called lossless compression. And for example, two of the students in your class, Cindy and Alan, are both working on lossless compressions, but for a different application, for maskless lithography and for lithography in general, for representing layout files for VLSI design. Another application of lossless compression, besides movies and cinema, where directors don't want to introduce any artifacts into their movies, is medical imaging. Doctors for generations have been trained on detecting tumors and abnormalities on analog images, and even though sometimes when you compress it, they agree that the image has been enhanced from the analog, and sometimes they don't even see any visual difference between the original digital and the compressed digital that's lossy. They still, because of lawsuits and because of the fact that the training in this medical establishment is entrenched into the system, that they don't want to have anything to do with lossy compression. So that's another field. Now, in contrast with lossy compression, if you stick to lossy compression, the compression ratios you get is very low. Could be, depending upon what data, what you're doing, it could be 3, 5, 10, or whatever. On the other hand, you could shoot at having what's called lossy compression, which means that you start with a file or data, and if it is audiovisual data, you're taking advantage of the characteristics of the ear and the eye, and you're saying, well, we can compress this, and it'll be a slight degradation in the output, but it's almost invisible to the eye. But in that case, this is called the lossy compression, and what happens is that you can trade it. There's a thing called rate distortion. So at a very low rate, the distortion, or the distortion means the difference between the uncompressed image and the original before you even did any compression. If that distortion is large, if the rate is very low, that distortion becomes large. If the rate that you're encoding for lossy compression goes up, as the rate goes up, the difference, that distortion, becomes smaller and smaller. So the rate distortion curve, as a result, is a curve that kind of dies down like this. So in lossy compression, where does the loss come from? Well, I start with an image, for example, and I take the transform of the pixels. I get discrete cosine transform coefficients or discrete Fourier transform coefficients. It comes from exactly what Wei talked about last time, quantization. You have a discrete Fourier transform that's, a number with n digits in it. You quantize it to one of m levels. It's that quantization process that introduces error both in the coefficient and in the final image. Okay, so having said all of these things, there's three basic questions that we try to address when we deal with compression. The first question is what to code, and let me explain what I mean by that. So let's say I have an image. I could be coding the pixels themselves. I could be coding the difference between the pixels. I could be coming up with predictions for each pixel and subtract that prediction from the actual value, generate an error, and code that error instead. Or I could just walk away from pixels. I could transform the pixels into a different domain. Hadamard, Welch transform, DFT, DCT, wavelets, just a transformation. And I could choose to code those. Or I could come up with a parametric model for my image. Let's say I'm only coding head and shoulders and faces. I have, 9 kinds of eyes, 10 kinds of lips, 12 kinds of nose, and I just send the parameters of how every person looks like, and with glasses or without glasses, straight hair, curly hair, black hair, blonde hair, that's a parametric model. So I could be coding those parameters. So in fractal coding, you're coding similarity transformations. That's the stuff that Barnsley came up with. So, one of the key questions is, what aspect of the image do we end up coding? Coding means quantizing, okay? And that's the main thing I'm going to try to address today. The second aspect, which I think Wei talked about a little bit last time's lecture, is once you've decided what to code, you want to figure out how to quantize it. So if if I've decided to code, for example, DFT coefficients or DCT coefficients, do I use a uniform quantizer? Do I use a non-uniform quantizer? Do I use adaptive quantization? And quantization is a process in which you start with a random variable and you discretize it into finite number of bins, and in order to tell the receiver, the decompressor, what bin it fell into, and at the other end, when the decoder has the information which bin it fell into, it has to choose a reconstruction level in that bin to represent all the values that lie in that bin. So for example, if suppose I was coding pixel intensity pixel levels, and the values are between 0 and 256, and I have a 2-bit quantizer, and I'm doing uniform quantization. So that's 128, that's 64, that's 192. So my quantization bins are, this is bin 1, bin 2, bin 3, bin 4. So at the encoder, I specify which bin each pixel fell into. This is like the simplest kind of compression you can ever imagine, but it's not very good. You specify what bin it fell into, and then send that information to the decoder. The decoder receives, okay, the information, for example, the pixel is in this bin. Then it has to figure out what reconstruction value to choose for this bin, and most of the time you pick a midpoint, and that's the reconstruction level. But if the probability distribution function of the original pixels in this bin was, for example, like this, you don't want to pick the midpoint. You want to perhaps pick something slightly to the left, right? Because you want to minimize the mean square error between the reconstruction level and in a statistical sense and the original pixel value, okay? Or you might want to decide to do non-uniform quantization. Say, look, I have a probability distribution function for my pixels, and I want to have 5 reconstruction levels. Tell me where the decision boundaries for my quantization bins should be in order to minimize the mean square error between the reconstructed value and the original. And that's called non-uniform quantization. And I think Wei talked about Lloyd-Max quantizers. That's a special case of, that's the most famous kind of a nonlinear quantization. So besides deciding what to code, the next most important question is how to quantize. So once you quantize, so essentially you start with a bunch of real random variables, real numbers, infinite precision on the real line. When you quantize it, now you have finite number of values. There's no infinite precision anymore. So now you have a discrete source with a discrete finite set of what's called alphabets, right? So whether I'm in this bin, this bin, this bin, or this bin, in this case, if I have 4 quantization bins, my alphabet size is 4. I have a source with alphabet size of 4, and now I have to code that. What does that mean? I have to bit allocate, allocate bits to each of these 4 letters in my alphabet. And the simplest way, again, is to say, oh, I got 4 letters, oh, two bits per letter, 0, 0, 0, 1, 1, 0, 1, 1, and that's a simple way of doing it. It's not necessarily the most optimal way. Why? Because some of the alphabets in the letter are much more likely to occur than others. Pretty much if you're coding the English language text, some letters are occur more frequently than the others. And if that's the case, how many of you have ever played with ham radio? Or know what ham radio is? Okay, you know what it is. So when you're doing ham radio, you assign shorter code words, if you will, to the alphabet letters that are more frequent, and you assign longer code words to the alphabet letters that are less frequent. And by doing so, you are maximizing what's called compression efficiency. Okay? So So there's a for every source with finite number of alphabets that emits a symbol every unit of time, there's an optimal lowest number of bits that can be used to represent that source. And that lowest number of bits is called entropy, right? So from an information theoretic point of view, that thing that Wei talked about last time, entropy, is the lower bound as to how many bits you need to represent a source with so many alphabets. And entropy has the following expression. I'll just write it down just to remind you. It's summation of pi log pi, where I ranges from 1 to n. Okay? So if I have the source with n alphabets, and each one has a probability of occurring, this half, 1/4, 1/3, etc., then I can compute this. And from an information theoretic point of view, I didn't prove this to you, but from an information theoretic point of view, it can be shown that that's the fewest number of bits it can be shown. Yeah, question. Sorry. Yes. Yeah. That's right, because log of pi is negative, so we put a minus sign. Okay, so you all know that, right? Everybody understands or remembers that from last time's lecture, from Wei's lecture. Now, just because we showed, this is kind of classic in information theory. Information theory is full of results that have lower bounds, but those guys never tell you how to achieve it or how to even get close to it. So people then start this. I mean, the classic one is Shannon's theorem, right? Which tells you at what signal to noise ratio, what bit rate you can get out of a channel. But the proof of it is a randomized algorithm. It doesn't tell you how to achieve it. But it's still a useful result, because when you go to bed at night, you know how far off from the optimum you are. And so if you're, let's say, within half a dB, you can rest at peace and not worry too much. But if you're 3 dBs off, you can say, oh, God, somebody else is going to discover a technique that get closer to the bound. So these bounds are kind of, they're not entirely useless. They're kind of useful in terms of letting us know how far off we're from the optimum. In any event, so there's multiple methods. If I have a source with so many alphabets in it, and now you know what these alphabet letters are coming from. These are the quantized values of our pixels, or our DCT coefficients, or our wavelet coefficients, whatever the thing is we decided what to code, right? They become our letters, okay? And now we got to do bit allocation. As I said, this is the lower bound on how many bits it takes to code a source like that. And the techniques that people have come up with is Huffman coding for bit allocation and arithmetic coding. And Wei talked about those as well. So it turns out that arithmetic coding can approach entropy a little bit better than Huffman coding, because it's more sophisticated, actually, because you got to do more computation. There's more calculations involved in this than there is in this. This is something that, by the way, it was invented at IBM in mid-70s, late 70s, and because IBM had all the patents on it, for years and years and years, it wouldn't be considered for standards until the patents expired in, I don't know, early 90s or somewhere along the way. And then it started getting into the standards, and it's now in lots of different standards. A prime example of what a patent does to a technique. It makes, even though it's better than this, people just don't use it because they have to pay royalties. Actually, another prime example of what licensing and patents and stuff stifles use is what? Is MP3. Why do you think MP3 is so popular? Not because it's definitely not compression efficient. I can swear to that. In fact, it's terrible in terms of compression efficiency. It's very old. It's like a 30-year-old standard. But the reason it's so popular, especially with your generation of kids, is because it's free. And actually Napster and those other guys made it even more free. They converted the songs into that format and allowed us all to download it. So anyway, I never downloaded anything. I don't even have a device to listen to. I have a Sony Walkman, actually, and I buy $13 CDs in it, and it's quite big. Actually, it doesn't fit in my pocket. Should convert to iPod. But anyway, So MP3 was successful because it was free, and arithmetic coding was not successful for a long time. Now it's finding its way into the standards. It's now in H.264. So in this scheme of source coding, right, you pick a letter from your alphabet, and you assign variable number of bits to each letter. The letters that are more frequent, you assign fewer bits. The ones that occur less frequently, you assign longer bits. The opposite of this scheme is called dictionary-based techniques, okay? And that is what I think Wei talked about. Ziv-Lempel is the prime example of it. And that's, and again, another classic case that it was not patented and it was used everywhere. The zip function you have on your PCs is this, Ziv-Lempel. And it was invented in 1977. And what it does is, instead of assigning variable number of bits to each letter in our alphabet, it looks at a stream of letters and assigns a fixed number of bits to variable number of letters. So it groups variable number of letters together and assigns fixed number of bits to it. And essentially the technique works by looking backward into the stream and figuring out where the repetitions occurred, and it points to that. So it's very good, for example, for text compression. I have a text, and the string of characters that occurred previously, instead of coding them again, I just send a pointer. You say, go so many spaces before and copy that to this location. So that's kind of the gist of it. Okay. And this is used all the time for many lossless coding kind of techniques. Okay. And again, the circuits that Cindy is building, for example, uses a variation of this. Vito Day, a student in my group, came up with an algorithm called C4 that combines some features of this with predictive coding, which I'll talk about today, and it's good for layout compression for VLSI designs. And now Cindy is building those in hardware. So that's kind of an overview of what Wei talked about. But what I like to mention is that besides, what are the metrics we care about when we think about compression? Well, we certainly care about compression ratio and compression efficiency. If I start with a 1 megabyte file, and if I have a fixed fidelity criterion, I say, okay, my distortion shouldn't be any more than this. Let's say I have a picture of Lena and I want to compress that, and I say my distortion can't be any more than X. Then ideally I'd like to minimize the rate. I want to compress that file as much as possible. That's obvious. But in some situations, other criteria come into play. For example, the encoding complexity or the decoding complexity. So why is that important? Well, you know, I didn't bring my cell phone. I didn't bring my cell phone. Anyway, if I'm taking a video with my cell phone and I want to send it like to my dad or my husband or my son or my mom or whatever, I have to encode it on the cell phone. And if the encode complexity is too high, so that after encoding a 10-second clip, I can't make any phone calls for the rest of the day until I go home and recharge my battery, then it's useless, right? Why is decoding complexity important? Well, the reverse situation. Like, suppose I've subscribed, you know, I'm on Singular, I want to watch, I forgot, what show do they have on their cell phones nowadays? I know Sprint and Verizon very well. I don't know, the one that I subscribe to, I don't know what it has. Whatever, Desperate Housewives. I want to watch some videos, music videos, okay? And if I stream the thing and it chews up too much cycles to decode, again, my battery would be dead. And in many applications, we as a nation and perhaps we as humankind, I can't really speak for the rest of the world, just in the United States, it's true that we are more consumers of content rather than generators of content. Right? I mean, think how many hours a day you watch, a week you watch TV or movies or listen to things, versus in how many hours a week you create content. Actually, you do create content. There's homeworks you do is content, but it's not like video and audio. That by content I mean like audio and video type thing. So because of that, because we mostly consume content and not so much generate it, many compression algorithms have been designed to be asymmetric, with the decode complexity being a lot smaller than the encode complexity. Okay, and that's true for MPEG-4. It's true for H.264. Well, H.264 is so complex I can't really speak about it, but it's true for most video compression algorithms. So they're highly asymmetric, with the encoding being much more compute intensive than the decoding. And but nevertheless, there are situations where the reverse is true, for video conferencing. For example, if you're doing video conferencing on your cell phone, the encode complexity also needs to be low so that the other party, so that the frames get encoded real time, so that you can have an actual interactive communication. That brings me to my next point, which is some differences between images and video. Before doing that, let me just say one more comment. The reason encoding complexity also can be large is that if you're a consumer of a content, you can do the encoding off time. It doesn't have to be real time. They can encode Desperate Housewives, or I can encode an entire DVD. That's a big business where encoding is done. DVDs are essentially MPEG-2 versions of the movies. So you can spend a huge amount of time coming up with a nicely encoded version of a particular 2-hour movie, put it on DVD, then send it to the video stores all across the nation for the masses to watch it. And it was worth it because you encode once. However, millions of people or millions of times that encoded content is viewed. So it's worthwhile to spend cycles, even though the encoding is more complex, because it's consumed so many times. It's worthwhile to spend a lot of cycles on it. So those are kind of one-way applications of video, where it's encoded once and then you stream it or you send it, you download it, and you watch it. The other kind of video application that's also very important is interactive video applications, two-way. Let's say I'm having a video conferencing. The same way as you're having an interactive phone conversations. You pick up your cell phone, you're talking to someone. There's FCC regulations of how much that delay should be in order for that interaction to be interactive and not be kind of like I give you a lecture and there's a 2-minute delay before you receive it, and then you answer my question, it arrives here 2 minutes later. So you want to maintain interactivity, so you have to have low delay. Does anybody know what that delay is for telephones? Is it a second? That's right. It's about 150 milliseconds. That's the FCC regulation. When they came up with the wireline telephone system in this country, a telephone from the East Coast to the West Coast, let's say Los Angeles to New York, should not have any more delay than 150 milliseconds. I don't know how many of you remember, when I was a kid, when we talked over the telephone on satellites, like from Iran to United States, for example, the delay was very substantial. It was seconds. You couldn't really have a conversation. Like I would say something, I would then really wait for 10, 20 seconds for the other party to hear it, because I knew they were going to answer. I would be silent to give them a chance to answer, and then they would answer, and then they would be silent for a few seconds to make sure that I have a chance. I mean, it really is no longer interactive. How many of you have done satellite calls to have noticed the delay? Well, this just shows the advances in telecommunication. So I must say I haven't called foreign countries. Well, I've called Asia many times now, and I haven't noticed any delays. So they've improved that quite a bit. But anyway, for when you're doing video interactive stuff, then there's two things. The encoding can't be done offline. It has to be done real time. So if a 2-hour DVD movie encoding will take you 5 days to do, it doesn't matter, because once you're done, you can mass distribute it. But when you're doing video conferencing, let's say, actually the video conferencing system you see every day in use is on television. When one reporter is talking to another reporter, they're essentially doing live video communication between them. In that case, the encoding complexity has to be low, or we can't, or we have to use simple encoding compression techniques so that we can encode real time, so that we still preserve the 150 millisecond delays that we're interested in. In that case, the encoder and decoder have to be symmetric. The encoder cannot be massively more complex than the decoder. Okay, so these are some general issues about compression. So we've talked a little bit about the problem of how to quantize, a little bit about how to code, and what I'm concentrating today mostly is to talk about the problem of what to code. Okay, and in particular, I'm going to start off with using just pixel domain information as the information that we encode. Actually, before I get on with the rest of the lecture, I just remembered an announcement that I forgot to say. Today at 4 o'clock in 405. Today at 4 o'clock in 405 Corey. Sorry, 405 Soda at 4 p.m. There's a talk on blind deconvolution. I forgot the name of the speaker, but do you remember?
It's Professor Aaron Hertzman.
Hertzman.
From Hertz.
From which school?
University of Toronto.
Yeah, so from University of Toronto. So he's actually asked the speakers, he's actually asked the audience to email him their motion blurred pictures so that during his talk he can process and show you the results. So I think it'll be a pretty interesting talk, and it's very relevant to the course because we just covered blind deconvolution like a week ago. So I encourage you to attend that. Okay, so what we're going to talk about today, right now, is really the problem of image compression, and more specifically the problem of what to code. Okay. So image compression. Problem of what to code. And kind of the first thing that we want to, the simplest kind of scheme that you can think about is pulse code modulation, or PCM. So the first class of techniques we deal about is waveform coding. And within waveform coding, we're going to consider PCM, which is pulse code modulation. We're going to consider DPCM, which is differential pulse code modulation. And then I think that's mostly it. And then we move on to transform coding. And really we talk about discrete cosine transform and Cahunan-Love transform. And then we'll move on and talk about subband slash wavelet coding slash, or all kinds of what I call multi-resolution coding. Multi-resolution coding. And then time permitting, actually, can you zoom out so the entire page is being seen in one shot? Okay, great, thank you. And then if there's time, we're going to talk about fractal coding. I'm going to talk about vector quantization. And then if there's time after, then right after we talk about this problem, then the next topic we talk about is video coding, which uses a lot of the stuff we talked about earlier for image compression, but we also need to talk about the problem of motion compensation and motion estimation. In other words, how do we take advantage of the redundancy across frames? And then, time permitting, I'm going to just concentrate on one standard, pick one standard, and just show you how we can mix all of these ingredients that these building blocks that we came up with in order um, to do to build a standard, to build an end-to-end compression system. So it could be JPEG, could be JPEG 2000, it could be MP3. Actually, there's one thing I didn't put in, and that's audio coding here. Okay, it could be MP3. It could be H.264 or H.263. Or it could be just regular MPEG-4, for example, MPEG-1, 2, and 4. So any one of these standards. Okay. So let me begin with the concept of pulse code modulation. But before I start that, I would like to talk about the metric that we're going to use in order to evaluate the different techniques that we're going to be using, right? So, in particular, so how to evaluate a compression algorithm? How to evaluate or compare various compression techniques? Well, what happens is you start you start with an image f of n1 and n2. That's your original, and then you pass it through some compression engine. Okay. And then out comes f hat of n1 and n2. So you can talk about mean square error between these two signals, or you can talk about what's called peak signal to noise ratio. And I'm going to explain what these are. Not that different from the expressions that we had, if you can roll up a little bit, from the expressions that we had when we dealt with restoration. So I'm going to define this normalized mean squared error as NMSE as to be in percentages, to be 100 times the variance of f hat of n1 and n2 minus f of n1 comma n2. Over the variance of f of n1 comma n2. Okay. So this is in percentage. NMSC is 100 times say 10%, 20%, etc. And then signal to noise ratio in decibels or dB is 10 log 10 of the inverse of NMSC in percentage over 100, and it's in dB. Okay, so you multiply this by 100 to get rid of this thing, so it's this quantity. So it's essentially 10 log 10 of this over that. So let me write that down. 10 log base 10 of this whole thing, which is variance of f over variance of f hat minus f. That's this SNR in dB. Okay. So just as a rule of thumb, you know, after you work for many years in compression, you have some numbers in the back of your head that tell you this signal to noise ratio is good and some numbers that are bad. So signal to noise ratios in 10s are terrible, 20 are bad, 30 is good, high 30s are very, very good. So if you got 30 dB signal to noise ratio, you're doing okay. If you're doing 35, 37 dB, you're doing really good as well. You have to be careful when you're dealing with compression to make sure your signal to noise ratio is not so high that it's not discernible to the eye anymore. Because at that point you're wasting your bits. Like for example, your eye probably can't tell the difference between signal to noise ratio of 40 and 41 and 42 and 43. And anything beyond that is it's so high fidelity you can't see it. Now, there's been a lot of work in image and video processing bashing signal to noise ratio as a metric. In fact, there's been studies that have gone on for years to try to replace it, right? Saying that this doesn't really correlate well with what the human eye perceives as a good image or as a good video. And oh my God, the Tektronix folks, there was a whole portion of MPEG-4 group of people that met every quarter for years and years, tried to come up with other metrics that reflect better the subjective quality. And it's sad to say that none of them worked. And that still SNR, if you look at ICAST or ICIP papers this year, ICAST being in France and ICIP being in Atlanta, every compression paper still talks about peak signal to noise ratio or signal to noise ratio. So that's something I would anticipate, 10 years from now, if I'm still teaching this course, there might be some advances and we might not be using quite SNR. By the way, what do you guys use in speech? Do we have any speech people in the room? Yeah, what do we use?
Actually, I don't know because that's not what I'm working on.
Okay.
I think it's like we investigate like the spectrum of
Right.
I think we just use the log energy, so more or less SNR.
Right. But they have another thing called MOS, mean opinion score, which is between 1 and 5. And they use that kind of all the time in their experiments. And it's much, see, the auditory system in human beings is a lot better modeled and characterized than the visual. So in fact, the ear pretty much, just as Howard said, acts as a spectrum analyzer. There's different frequency bands, and your cochlea acts as a spectrum analyzer. It's like a filter bank, right? It produces output at different frequencies. So essentially, your ear is, it's as if you went and bought a Tektronix spectrum analyzer. It's just that it's smaller and it fits here and it sends them. The eye, on the other hand, is absolutely not a spectrum analyzer at all. Very little understood about it. Okay, enough of the metrics. So I'm hoping that today I can get done with PCM and DPCM, and then on Friday I will cover DCT and KLT, and then next Wednesday the subband and wavelet multi-resolution stuff, and then next Friday the other kind of portion. Okay, so let's talk about pulse code modulation, the simplest simplest way of doing pulse code modulation, simplest way of encoding anything. So the basic idea is this. So this is the encoder, and you have f of n1 and n2. You pass it through a uniform quantizer, and out comes f hat. It's very, very simple. It can't get any simpler than that. Okay. However, it's terribly inefficient. It requires 5 or 6 bits for the signal that you do this to look good. If you just if you were to use 2 bits per pixel, if you were using this technique, you get terrible contouring effect. So let me just show that to you. You can zoom in to these pictures. Okay, so this is the original Lena image, 512 by 512. And this is the PCM quantized version of it when you're spending 2 bits per pixel. And initially you might think 2 bits per pixel is low, but let me warn you, JPEG 2000, you can get pictures that your eye is indistinguishable from the original at 0.125 bits per pixel. So 2 bits per pixel, in fact, is terrible. It's awful. Anyway, so I'm hoping to show you some of the techniques. I mean, JPEG 2000, as I said, uses wavelets, so we'll hope to get to that. But here's the thing. 2 bits per pixel, you see all the contouring. So even through our monitor system that's leaves something to be desired, you can see how terrible this image is. So so what do we do to fix that? So I showed you figure 1022, A and B in Eennlb's book. So how to fix that? One way to do it is to add what's called Robert's pseudo-noise technique. And this is a technique that's routinely used in engineering, and it's not only used for image compression, it's also used for A to D design. How many people do we have here that do analog to digital conversion or have experience doing that? You basically add dither at one end in order to randomize things, in order to get rid of the contouring effect that you just saw. And the way that works is like this. So this is the encoder. So in this case, at the transmitter side or at the encoder side, let me move on to a new sheet. You have f of n1 and n2. And what you do is you add this noise W of n1 and n2 to the signal, and then pass it through a uniform quantizer. And you make sure that this pseudo-random noise, which is predetermined ahead of time, is also known by the receiver. This is not signal dependent. It's something, it's some sequence of random numbers I've cooked up ahead of time, and I want to make sure that that's available. This is the boundary line between my transmitter and the receiver. So in this side is the transmitter, and this side is the receiver. And RX doesn't stand for prescription, it means for receiver. And how do we do that? Well, you send this guy here, you have WN1 and N2 here. Because you added it at the receiver, you subtract it because you added it at the transmitter, you subtract it at the receiver. And out comes F hat of N1 and N2. Okay? And generally speaking, so inherent to this scheme is that W of N1 and N2 is known both at the receiver and at the transmitter, okay, ahead of time. And usually people, you choose W of N1 and N2, you can use different noises, but typically you use it to be a white noise sequence with uniform PDF. In other words, PW of W naught is 1 over delta for W naught between delta over 2 and minus delta over 2, and it's 0 otherwise. Pick a random number between 0 and delta. Okay, where in this case delta is the quantization step size. Okay, so you add a noise within the quantization step size into the system, and at the other end you subtractive. And I'd like to show you a figure in Eennlb's book that kind of explains this process as an example. So figure 1021 in Eennlb's book pretty much covers that. So you can zoom in, please. So this is the amazing thing is that he applied this technique to a speech sample, even though this is an image and video processing code. But the concepts are easier to understand for one-dimensional signal. We'll just concentrate on that. So this is an original speech signal. And this is what happens if you quantize this at 2 bits per sample. So you pick the maximum, you pick the minimum. 2 bits per sample is 4 levels of quantization. So so here you do it. There's 1, 2, 3, and 4, right? 1, 2, 3, and 4. And this is a function of time. And this is what happens if you now add the white noise of the characteristics that I just talked about to the original signal, and then quantize it to 2 bits per pixel, and then subtract the white noise at the other end. So that white noise is known, again, to both transmitter and receiver. So you can see this is a much more faithful representation of what you had here than this is. And finally, there's a way to kind of improve the fidelity or the good-lookingness or the visual appearance, that's the word, the visual appearance of the final signal. You can do some more low-pass filtering. It's called post-processing on the reconstructed output, and get something like this, which, if you can zoom out just a tiny bit, that looks even closer to the original than this did. The reason being is that in the process of adding noise and quantizing and removing noise, you've added a little bit of a high frequency unintentionally. So if you do low pass, a little bit of noise removal type techniques like low pass filtering, then you can do better. So just so that you can see what kind of performance you get out of this thing, look here. So this is the original Lena. This is the 2-bit quantization on an image without doing this Roberts noise technique. This is if you add the Roberts noise technique, but don't do any post-processing. And this is with Roberts noise and with post-processing. And actually, I must say, looking at the picture here, I see a big difference between these two. So the noise processing actually does something. There's a lot of dots, high-frequency dots on the face here that have been blurred out over there. Okay? So, so coming back here, so 1021 and 1022 of Eennlb's book. So, you can improve visual quality by doing what's called post-processing or to reduce noise. Okay? And by the way, this post-processing to reduce noise is an integral part of a lot of video compression standards and techniques. Every time you do apply discrete cosine transform, you get blocking artifacts. You need to do post-processing to remove that, to smooth it out so the eye doesn't see these sharp boundaries of the blocks. Okay? All right, so PCM is just very trivial. It's primitive, it's old, it's non-sophisticated, etc. So you can become a little bit more sophisticated by using what's called delta modulation, another waveform coding technique. And even though we're going to apply it to the pixel domain, when you get to video and when we talk about motion compensation, delta modulation and DPCM, differential pulse code modulation, are more or less the same ideas we use to take advantage of the redundancy across the temporal dimension, across frames. So how does the delta modulation work? Again, here's the transmitter. You start with f of n, and you do 1 bit quantization or however number of bit quantization you want to do. And what comes out of here is E hat of n, which is either delta over 2 or minus delta over 2, depending upon whether the signal was above a threshold or below a threshold. This is a 1-bit quantizer, right? And then you look at the previous sample, f hat of n minus 1, that you reconstructed at the receiver, and you subtract the way you generate this signal. Sorry, I should have drawn this first before going there. So you assume you have access to the decoded and encoded version of the n minus first sample. You subtract that from the current nth sample. You generate an error signal E of n, 1-bit quantize it. That's the quantity you send to the receiver. Okay. And in order to come up with, the transmitter also needs to keep track in order for it to have access to f hat of n minus 1. At every step, it has to build f hat of 1, f hat of 2, f hat of n minus 1, f hat of n. And how does it build f hat of n? Well, the same way as the receiver does, which I'll show in just a second. Basically, you add e hat to f of n minus 1 in order to come up with an estimate of f hat of n. Not estimate, in order to come up with f hat of n. And this step, can you roll up a little bit? This step that I just did shows you what the receiver has got to do, right? The receiver essentially starts with, it receives e hat of n, it adds to it the f hat of n minus 1, and out comes f hat of n. And then how does, from f hat to f hat of n minus 1? Well, it goes through a delay function. Z minus 1, delay function, to get that. So these are the block diagrams. Let me just explain intuitively what's going on. Essentially, the transmitter and the receiver both have access to the previous sample, f hat of n minus 1. Okay? Of course, the transmitter has access to f of n minus 1, the actual f of n minus 1, without any quantization, errors, or compression. But we don't want to use that, because otherwise the two loops at the transmitter and receiver will get out of sync. They drift apart from each other. So the transmitter and receiver, they both work with this f hat quantity. They know what the reconstructed value of the n minus first pixel is. The transmitter gets the actual n pixels, subtracts it. It uses the n minus first reconstructed value as a prediction for that. It subtracts it, gets an error, quantizes it, and that's what it sends to the receiver. So the receiver now has e hat of n, but the receiver also had f hat of n minus 1, so it adds these two things as an estimate of f hat of n, right? Because of the way the transmitter did. The transmitter subtracted these two to get e, or e hat. The receiver does the opposite of it. It adds e hat to this to get f. So you have a loop in the transmitter and a loop in the receiver that are in perfect synchrony with each other. They're both tracking f hat of 1, f hat of 2, f hat of 3, etc. You can imagine why things would go out of whack if instead of f hat, the transmitter would use f of n minus 1. Then the two things would drift apart and the errors accumulate. Okay, so what are some of the simple equations that govern this thing? Well, I mean, E of n is f minus f hat. So let's just write that down. E hat of n is just the quantized value of E of n, which is delta over 2 if E of n is larger than 0, and it's minus delta over 2 if E of n is smaller than 0. And the last thing that we want to talk about is actually, let me not use this notation here, because I want to use Q for something else. So if E hat of n is related to E of n through this equation, and if I talk about quantization noise, which is defined as f hat of n minus f of n, that's how much error, due to these delta modulations we've introduced, it's basically E hat of n minus E of n. Okay? So what are some challenges in this system? How many parameters do we have in designing this system? Essentially delta. And so the big question that comes up is, how do we pick delta optimally? And there's no really good answer to that, simply because of the following. I think I'm just going to show figure 1026 of Eennlb. If you pick delta too small, you get one problem. If you pick delta too large, you get another problem. So there's this compromise that you have to kind of come up with. You might say, well, why is it that for... So let me explain what I mean by that. Let's just zoom in into this picture. Okay. So this is a signal that's slowly varying in this region. This is the x-axis as a function of space. I'm moving from left to right on my image, for example, right? And this axis is the intensity of the pixels, right? In this region, the dark black line here is my signal value, right? So in this region, the signal is slowly varying, and then here the signal is fast. It hits an edge. The intensity changes very rapidly. So in this region, if I've picked delta is essentially the height from here to here, the change here. So I've picked this particular value of delta, and in this region, what I end up getting is what's called granular noise. The signal is constant, and yet I'm going to represent it as this value, this value, this value, this value. It's going to go up and down. So this is what's going to cause granular noise, right? And here, the signal is varying too fast, and I've decided I have to go up, 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 but I can't catch up with the rate it went up. So this is called slope overload. And you can see both of those phenomena if you look at figure 1027 in Eennlb's book. Okay? So on the left-hand side, you have a delta modulated signal where delta is chosen to be 8% of the overall dynamic range. So if the pixels are from 0 to 256 intensity values, 8% of 256 is, what is it? 20. So delta is chosen 20, for example. And here, if delta is chosen 15% of the dynamic range. Okay? So in this case, delta is too small, and you can see the edges are extremely blurred. When there's a big change from in the intensity, the slope overload thing that we were just talking about happens, and therefore the edges become very blurred. Here, the edges are less blurred, but in some constant intensity regions, like here, you get a lot of granular noise that wasn't in the original signal. And just so that you know, the signal-to-noise ratio in this case is 8 dB, and in this case is 10 dB. And moving here is showing that so you can improve. Yeah, actually, I'm going to skip that image altogether. So delta modulation. So 1026 and 1027. So delta modulation has this problem of how to pick the value of delta in an optimal fashion. Okay. So next, what we move on to is DPCM, which is differential pulse code modulation. And let me draw the kind of the block diagram of this system, and intuitively explain what it does. And then on Friday's lecture, I'll drive all the. Maybe we can do the equations today too. Equations for it. So at the transmitter, once again, I have some predictions for f, and I call it f hat of, or f prime of n1 and n2. And I subtract the actual value of the pixel f of n1 n2 from the prediction value, and I get an error signal e of n1 and n2. And then I PCM quantize that, so you can see that this is built on top of the PCM. And what I get out of it is e hat of n1 and n2, right? And I send that to the receiver. And the receiver here, maybe I should do the receiver on a different sheet because I need that space. So the receiver gets this guy e hat of n1 and n2 from this n, and it adds to it the same prediction f prime of n1 and n2. So here we subtracted it at the receiver. After it quantizes it, it adds it up. You can imagine if this box didn't it didn't exist, this would be a perfect kind of a system. And then out comes f hat of n1 and n2. So the question is, how do we come up with a good prediction? And the answer is, you can use any technique that you like, as long as it makes a good prediction. And how do we decide a good prediction? Well, a good prediction is one where, with fewest number of bits, it has the highest fidelity. I mean, gee, we're doing compression. That's the most obvious thing to do, right? So you can use linear predictions, you can do nonlinear predictions, you can do ARMA models, autoregression. I mean, all kinds of things. So we kind of leave this box here as just prediction. But this prediction, the only thing we need to impose on it is, because receiver and transmitter both need to have access to f hat, this prediction at both places, this is also based on prediction. So just draw the prediction box here as well. But the thing to remember is that both of these predictions should be done based on values that are available both at the transmitter and the receiver. So this prediction cannot be based on f values, the uncompressed raw pixel values. It has to be based on f hat values. So all I say here is that this is based on previously coded pixels. For example, f hat of n1 minus 1, comma n2. So if you're doing it, if you're encoding your picture in a raster scan, left to right, top to bottom, you've already done this pixel. The transmitter and receiver both have access to that, so you can use it. F hat of n1, comma n2 minus 1, f hat of n1 minus 1, comma n2, etc. And how does, so, and this is the same thing here. This prediction is also based on f hat of n1 minus 1, comma n2, comma f hat of n1, comma n2 minus 1, f hat of n1 minus 1, comma n2 minus 1, etc. Sorry, this is n2 minus 1. I already had that pixel. And so, again, the thing to remember for both of these schemes is that whatever algorithm you use here, it has to be the same algorithm you use down here. So the transmitter and receiver ahead of time have agreed how they do the prediction based on previously coded pixels. And where do these previously coded pixels come from? Well, how does the transmitter figure out what these f hats are? Well, it has access to the e hats that it generates. And if it adds the e hats, just like what the receiver does, it adds the e hat to f prime to get f hat. So it has the e hat to the f prime here to get f hat of n1 and n2, right? And then it can use various delay elements here in order to figure out all these other quantities. But you have to be scanning your image in such a way that these are available. And how does the receiver know what these guys are? Well, these are previously encoded quantities, so essentially through a delay box, and then you can know all these other values. Okay. So one of the questions that you might ask is, okay, you just told me I use these pixels to predict. How do I do that? Well, you can come up with any prediction function you like. You can even come up with a table lookup. If this pixel takes on this value, that value, and that on the other value, then the prediction is this, etc. You can do anything complicated, but something simple that people have come up with. So how to do prediction is linear combination. Okay, so you can just say that um, f prime of n1 and n2 is just a linear combination over k1 and k2 of a of k1 and k2 times f hat of n1 minus k1 comma n2 minus k2. So basically all I'm saying is this is a linear the predictor is a linear combination of the previously coded pixels, where k1 and k2 you might say, okay, for what values of k1 and k2? Well, we generally we call it r sub a. They have a region of support of r sub a. Okay, and the goal is, so how do we pick? So the question is how to choose the a coefficients. So well, we better pick a criteria and minimize it or maximize it or optimize it in order to do that. Well, what is it that we want to what is it that we want to minimize or maximize? Well, we want to make sure that what happens? We want to make sure this prediction is as close as possible to the f value, right? Coming back to this picture here, no, sorry, to where is my transmitter? I lost it. Oh, here. Yeah, to this picture here, I want to make sure that that the energy, the expected value of this signal is the variance of this signal or the energy in this signal is as small as possible. Okay, so one thing reasonable to do is minimize. Why? Because if the variance of E is small or the energy in it is small, it takes fewer bits to quantize it for a given fidelity level. That's something that when I first learned compression, it wasn't ever obviously stated. So we want to minimize expected value of E squared of n1 and n2. In other words, the expected value of f of n1 comma n2 minus the double summation of a k1 k2 f hat of da 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 da, etc. This whole thing here, but the whole thing squared. I'm going to minimize that. I think I'm going to stop because there's a lot more and there's a lot of examples I want to show next time. So just we'll stop at this point, and on Friday I'll pick up this. So you can easily imagine with some change of variables here, and so just solving a linear system of equations, we can figure out what the best values of a's are, and that'll be one thing that people use all the time. So I'll see you all on Friday. Hi, Cindy.
Yeah, so I got your email from Laura.
Right.
Yeah.
Right.
So I think the problem is that yes, I can find her some help in BYC and
Right.
yeah, but the first thing is that we have to get the data from him.
Yeah, I don't know what data you're talking about, and I don't think he knows what data you're talking about. In his email, he says that he thinks he can get all the stuff from the design itself.
Right, but we never got the design itself.
Well, you don't necessarily have to meet with him
Okay,
to ask for things. He's very responsive with email.
okay,
So if you never got the design itself, so send him an email, CC me in all your communications. Say, Bora, I need the design itself.
okay.
Can you send me?
Let me take this.